Well, today we're here to talk about a brief overview of statistics and some, I think, where a lot of us get hung up. I mean, all of these sessions are about where we all get hung up, right? But, you know, we think we've got statistics and we look at the numbers and we're like, oh my gosh, this looks so great. Or we know in our hearts that there's been a big change and we know that this is awesome and that this is going to revolutionize the world. But then we don't know what to do with the statistics and we don't necessarily have the skills. And our biostatisticians are often overworked and harder to reach. But Catherine Shaver is here today. She is a biostatistician here at Carilion, and she also has a faculty appointment at Jefferson, correct? Adjunct faculty position at Jefferson. And has, anytime you mention Catherine Shaver, anybody who can get to work with Catherine Shaver says outstanding things about her knowledge base and her willingness to help and to really get invested and really loves trying to help you all love your research as much as they love research. She's a biostatistician with the HEART, which is a health analytics research team. It's a new name. They've switched names a few times, but this is what they are now. And she's here to talk to us about a brief overview of statistics. So please join me in welcoming her.
Thank you. Well, this is always kind of hard because I feel often like I'm cramming one or even two semesters of a course into 50 minutes. So we're going to go really fast. And the main thing I think that I hope you come away with today is just kind of an overview, not only of statistics, but also what services are available to you through the HEART team, and, you know, that you feel comfortable coming to us for any questions that you have. I always joke that if you can show even the slightest affiliation to Carilion, we'll help you with your research. It doesn't matter if you have money or not. If you're applying for a grant, that's great. If you don't get it, we'll still help you. So we do really, want to get involved and help you out as much as possible. And it's true, we do stay busy, but we're working hard on that and crossing our fingers that someday we might expand a little bit. Okay, so these are just the objectives of the course: to be able to tell the difference and know a little bit about a few different statistical techniques, and to be able to have a guess as to what statistical test is appropriate for what kind of research question you're looking at. And then and we'll probably focus less on this because within the time constraints that we have, it's really not as important, but just to sort of flash up at least a few ideas of what your database should look like as you're building that to make it easier for us to analyze the data. So why should you care about statistics? What can statistics do for you? Well, obviously, it's going to be difficult to be published. I guess those first two bullet points kind of go together. Statistics are really what lends the credibility to what is going on, to the conclusions that you draw with your study. And that, of course, is most of the time, at least for anything other than case report type stuff, that's going to be necessary for publication. So those are two really obvious reasons, I guess, that statistics would be important, but possibly the most important is that it makes you an informed consumer of other people's research. So how many of you, I know I see some familiar faces and know some people, but how many of you are actively working or have plans to work on your own research project? Or even just a little bit of an interest. Okay, but even if you didn't, so that's most of you, but even if you didn't, everybody now needs to understand, research and be able to apply that to their practice. So if you can evaluate the statistics in an article that you read. It will help you decide, hey, should I apply this to what I'm doing? Is there a policy we should change? How does this fit in with our care here at Carilion? So there are two categories of statistics, descriptive and inferential. And we'll talk about descriptive statistics first. So kind of as the name implies, they're used to summarize a set of data. I usually think of descriptive questions that can be answered with descriptive statistics as being sort of the what, who, how many, sometimes where and when, not always why. Why is more the inferential piece that we'll get to in a minute. But especially just sort of what's going on. Sometimes there are times when you want to look at a sample of our patients and just kind of get a feel for what is happening with a particular subset of patients. So that's where descriptive statistics come in. And so they include things like the N, which is the sample size, the mean, the median, and the mode, which are all three measures of central tendency. So they tell you something about what most of the people in the sample are doing. The standard deviation and the 25th and 75th percentiles deal with the variability. So it's not only important to understand things like the mean, but you want to know how spread out the data are. Are they all kind of similar and clustered around the mean, or are they really spread out? And so that's what variability gets to. And the minimum and maximum can be used to just get a feel for the range of the data, which really is also part of the variability. And then frequencies are just usually a tabular kind of format that help you understand the counts and percentages of the different variables that are in your data set. So here's an example of a table of descriptive statistics. And I should also add that even if this wasn't the main focus of your study, this would be a part of every data analysis or every study that you conduct. In nearly every journal article, Table 1 contains the descriptive statistics that tell you what's going on with the sample. And I can't stress enough how important it is to know your data. So especially in a big data set where you may not automatically have a feel for what's going on, the descriptive statistics really help you understand that, and then that helps you later when you may run into questions or problems or things you didn't anticipate, if you kind of have a good grounding in your sample before you get started. So anyway, this is just an example of LDL cholesterol in a sample of 150 patients, and you have these things that we talked about. Q1 right here is the 25th percentile. The median is the same thing as the 50th percentile, so half are above and half are below that value. And Q3 is the 75th percentile. And so this just, again, kind of helps you understand what's going on. So there are also some visual, graphical ways to understand your data that are also descriptive, and a scatter plot is one of those. In this example, we have minutes of exercise on the x-axis and LDL cholesterol on the y-axis, and these are made-up data, so it would probably never look this perfect in real life. But you can see by looking at this that as the minutes of exercise go up, the LDL comes down. So if we pick a point right around in here, these people would be exercising about 150 minutes, I guess, a week, whatever the time frame would be. And whoops, their LDL was really low at like probably around, I don't know, 105 or something. And this is, the reason scatter plots are nice is they show you the shape of the relationship, and you can easily identify that this is a linear trend, that this looks, there's no real curve going on. It's very nicely linear. And you're also able to easily identify any outliers. And none of these points here are really too far away that I would consider them outliers. But if you had a point up here in this quadrant of the graph, or one down here in this quadrant, you would check that out. You would see if maybe it had been a typo or a data entry error. Try to figure out what's going on with, any outliers that you see. So then another graphical way of understanding the data, I'm sorry this is a little bit pale, is a box and whisker plot. And this is actually, is based off of real data. I'm not sure really why anybody would look at this, but I was trying to find something that made a nice plot. So what we have here is, this is in a sample of geriatric trauma patients here at Carilion, and this would be their etiology, their mechanism of injury, basically. And so you have fall, gunshot wound, motor vehicle accident, motorcycle accident, other pedestrian accident, and stabbing. And then this is their age. And so I wouldn't try to draw any conclusions from this, but it's maybe a little bit how you would expect. The lines across the box are the medians. So the median age of falls is higher than anything else, which is consistent with what we would expect. I can't tell you what actually is in other. I guess that's everything else. And so you can see that there are a few outliers here. So a little more about how this works. The box itself, the lower end of the box is the first quartile, the 25th percent, and then this upper end is the 75th percent, the third quartile. And then these ends of the whiskers, the formula that is commonly used for this is 1.5 times the interquartile range. So without going into a lot of detail about that, this is not actually the end, this is not the maximum and the minimum, because as you can see then we still have some outliers beyond that whisker. But so you can just get a sense of how big the 25th to 75th percentile is. It's a lot smaller for motorcycle accidents, which tells me that in the geriatric population, I guess at some point people quit riding motorcycles, right? And so they're kind of crunched down with not as much variability. But you can, you could make whatever conclusions you wanted to out of this. But this is an example of a box and whisker plot. Okay, so a histogram. This is really nice for figuring out if the data are normally distributed or not. And that is the main reason that I use one, is just to figure out what the shape of the data looks like. And so here you can tell that this has a pretty decent bell curve shape, which suggests that the data are normally distributed. Now, why do we care about that? You might say, well, it doesn't really matter. And it doesn't for the most part, except that it helps us figure out what statistical test to use. A certain, there's most statistical tests depend on an assumption that the data are normally distributed. And if they're not, you need to know about it so that you can choose an appropriate test, which would be called a non-parametric test that takes that into account. And that actually happens fairly often because a lot of variables in healthcare are not normally distributed. And I actually have an example of that here on the next slide. Length of stay is something that will never be normally distributed, right? We don't have people who are, we don't have that nice bell shape with tails on either side. Most people are down here in the 3 days or, whatever, 2-3 day range. But then we have those people who are here for a very long time. And so that causes this long tail out to the right, which another word for that is skewness. So whenever I do a study that involves length of stay, I know that I'm not going to be able to use regular parametric tests for that variable, and we'll have to make some adjustments for that lack of normality. Okay, so that's kind of a pretty good overview of descriptive statistics, and now we'll move into inferential, which is what people usually think of when they think about statistics. If they think about statistics, I guess most people probably don't think about statistics very often. But anyway, this is when you use data from a random sample to make some conclusions about the larger population. So we can't often measure the entire population of interest. Especially, my background actually is not, my degrees are not in statistics, they're in psychology and human development. So I was trained in studying things about human behavior that apply to everybody on the planet, basically, right? And so in those fields especially, you almost never are going to be able to measure the entire population, because the population really is everybody. In healthcare, there are some times where, depending on the focus of the study, you can approximate a population, or especially if you're interested in, only studying within our organization, then it is possible sometimes to have data on the population in terms of what's available to us. We may not have, we can't access data from patients elsewhere, but we're getting all the patients who fit the criteria within Carillion, then sometimes we actually end up looking at that as a population and not as a sample. But most of the time, it's going to be based on a sample. And so there are two kinds of inferential statistics, and that is estimation and hypothesis testing. So estimation, I would say, is the less common of the two. It tends to be when somebody comes to me and says, oh, I want to know approximately what the rate of this thing happening is in this group of patients. And they're not really looking for a difference. They're not really, checking to see if something created a change or a difference. They just kind of want to know, how often does this happen? And that tends to be an estimation question. So what we're doing in those situations is we're looking at a sample and we're calculating a result, an estimate, and then we are putting a confidence interval around that to say, how good is this estimate? If I take 3 people and I come up with, their age or whatever, that 3 patients, and I look at their age and I say, well, the average age of patients at Carillion is, 20. Well, but if I only looked at 3 people, we're not going to have a lot of confidence in that statement, are we? So by having a large enough sample size and doing some other calculations, you can figure out ahead of time how many people you need so that you can feel good about saying, well, the estimate was such and such, and I think that's pretty close to what it really is in the population. So that's what estimation is about. And then hypothesis testing is what people, again, commonly think of when they think about research and statistics, I think, which is usually trying to figure out if 2 or more groups are different from each other, statistically significantly different, and that usually is associated with a p-value. And so that tends to be a lot of what we do with research here at Carillion. So the type of data that you have, as it says, will influence the choice of your statistical technique. So that's a good place to start, is figuring out what kind of data you're working with. So categorical data are data that are labels rather than numbers. So a simple example would be something like hair color, brown, blonde, black, red, gray, blue, whatever. You could use numbers to indicate those different categories, but the numbers themselves would have no meaning. You can use the words, because there's no numerical value to having, blonde hair versus red hair. And so that would be actually an example of nominal data where there's no ordering to those categories either. It's just different categories of hair color, and there's no relationship, no numerical relationship, and so that would be a nominal level of data. And then ordinal is also still categorical, but now there's an order to it, a natural order to it. And a good example of this is a pain scale. So none, mild, moderate, severe, very severe. So each of those categories indicates increasing amounts of pain, increasing levels of pain. But you notice it still doesn't say anything about a numerical relationship between those categories. So we would never say that very severe pain is twice as bad as moderate pain, right? Because we know that's different for everybody. And there's, with just measuring it this way, there's no way to mathematically relate those categories. We can only say that very severe is greater than moderate, but we don't know by how much. Then we get into continuous data. And so this would be data with potentially an infinite number of values. So this would be things like weight, blood pressure, blood glucose, lab values, temperature. It can be scores, different scoring systems that we use for, depression or just whatever things. As long as the numbers have meaning, it's quantitative, and if you think of it as having a position along a continuous number line, then that's very different from the categorical that we just talked about. So there are two types of continuous data, interval and ratio, and the difference in that is ratio actually has a true zero. So the most commonly used example to explain this is temperature. When temperature is 0 degrees, does that mean that there's an absence of heat, like a complete absence of heat? And I'm talking about Fahrenheit and Celsius, actually, so because that's an important distinction. So no, right? We know that temperature goes below 0, and it doesn't mean that at 0 there is no temperature, there is no heat. Whereas something like almost any lab value lab values are a good example. So I guess like if you had, a lot of them you would be dead if you had a 0, but that's conceivable that if you measured a 0 for something like, red blood cells or white blood cells or whatever, then you literally don't have any. It is the absence of that thing, and so that's a true 0. And so that's the difference between interval and ratio, but in practice, we often treat those the same. The analysis methods are pretty much the same, and that's not something that we worry about too much. Okay, so then some more terminology. Dependent versus independent variable. So the dependent variable is the thing that you think is affected by whatever it is that you're studying, a treatment, an exposure, or some other characteristic. It can be the variable that you're trying to predict, and it's a lot of times referred to as an outcome variable or a response variable. So that's your dependent variable. It depends on something else. Then your independent variable is the thing that you're really trying to isolate to study. You think it influences the outcome variable. So it's It's independent. It can be, again, a characteristic that, say, the patients bring to the table, like their gender. It may be something that you do, like assigning them to a control group versus a treatment group. And it is often referred to as a predictor or an explanatory variable. So now that we've been through all that, types of data, and independent and dependent variable, this slide actually gives you a little bit of a hint as to what statistical technique may work for your data. So you can't apply certain statistical methods to certain questions or variables because they don't work. It's not, you can't do, for example, you can't do a t-test if all your variables are categorical, because a t-test is measuring the difference in means in two groups. So if you can't get an average of your numbers, which you can't with categorical data, then you can't do a t-test. So this is often helpful in terms of just narrowing down. If you know whether your outcome variable is categorical or continuous, and you know whether your independent variable is categorical or continuous, you can kind of get a clue as to what, statistical technique may work. Now, there are a whole lot more that don't fit on this slide. So this is not meant to be the end-all be-all of how to, these are not the only statistical techniques you can use for your data, but this kind of puts you in a ballpark. Okay. So now, power analysis. This is always a hot topic and is oftentimes our first, as biostatisticians, it's our first contact with a client. So they have their research question. We can't do that for you. You pretty much have to come up with that on your own. But then after that, that's the time to get in touch with us. And oftentimes people come, needing, hey, this is what I want to study, and I need to know how many people I need to have in my sample to have enough statistical power. So let's break that down a little bit and talk about what all that means. Statistical power is the ability to detect an effect that actually does exist. So in the population, that larger population that we can't measure, if an effect actually does exist, you want to be able to detect it with your study, right? You hope that your study finds that and mirrors what's going on in the population. So this is something that we look at beforehand. We try to ensure that a study will have adequate statistical power ahead of time, before you collect data, before you do any analysis. I sometimes have people come to me and say, well, this, we've analyzed the data, this finding was significant. Did I have enough power? And I say, yes, because if you found a significant result, then automatically you had enough power. What you're trying to avoid with a power analysis is you don't find it to be significant in your data because usually you didn't collect enough data, and so it looks like something might be there, but it's not significant because your sample size is too small. So if you're, at the end of the day, when everything's done, if your results are statistically significant, if that p-value is less than 0.05 or whatever criteria you've set as a cutoff, then you don't have to worry about power for that question. You know that you had enough power.
Can I ask you a question
Yes.
about that?
Yes.
Because I teach that to our pharmacy residents, and they tried to give me some pushback at some point. Are there any exceptions to that rule when we're evaluating, now this isn't my own research, but when I'm evaluating research and you see that there is a difference statistically, and I'll have them go back and look at the numbers and they'll say, well, we weren't powered though, and so they question things, but is there any exception to that statement that you know of?
No, I don't. I mean, is it a scenario where they have more than one question? And like more than one research question as part of the project? Or it's just...
I'm saying now that we're evaluating somebody else's published research.
Oh, gotcha.
So we're evaluating and we'll see that there's a difference, and they'll go back to the original statistical analysis plan and say, but we didn't have enough patients. And in the study, when I say we, I'm saying the study didn't have enough patients in it. They didn't reach their power that they wanted because they didn't enroll enough patients. And I always push back to say that if they showed a difference, I don't care they had power. I've had some pushback on that from some of my young trainees, and I don't.
That's interesting. Just because, just very specifically, statistical power is all about and really only about avoiding type 2 error.
Right.
So without going into a big long, but there's type 1 and type 2, and type 2 error is defined as failing to find an effect that actually does exist. So if you found the effect as significant, you're not committing type 2 error. You might be committing type 1 error, and I'm not even going to try to put that in words because I think it might come out of my mouth wrong. But if the results are significant, then by definition, you can't be failing to find a significant effect.
Okay.
So I'm surprised at that because,
I have pushed forward with the way that I believe it. I've asked them to provide me some sort of documentation or evidence where they were taught this or why, but
yeah, I'd be curious to know that too.
I just figured I'd ask the experts.
Well, but I was always taught never to do a post hoc power analysis either. So that's all supposed to be done ahead of any data collection or anything like that. And there's, I've read many articles that say there's never a good reason to do post hoc power analysis. Now, that doesn't stop people from asking for it every now and then. And I usually tell them no. So I don't know if that would have anything to do. I guess if somebody thought post hoc power analysis was okay, maybe then you could go back and pick apart the power using the data from, I don't know. I would tend to agree with you that if you have a significant finding, then power is not an issue. So that's a good question. Thank you. Okay, so sometimes I get a vibe that I stress people out when I'm doing their power analysis because I have to ask them a lot of questions. And so this bullet point here, power analysis is a blend of science and art. It really is, and it's not worth getting stressed out about. Oftentimes, we don't know exactly what's going to happen. We don't, there may not be published results to look at for information to answer all the questions that I will ask, and I'll get to these on the next slide. I'm going to do this right now. Okay. So these are the things that I ask people about, the things that we need to know in order to do the power analysis. So first of all, you actually have to know how you're going to analyze the data because the power analysis calculations are specific to the technique that you're going to use to analyze the data. So I actually use some software called PASS, P-A-S-S, Power and Sample Size. It's the parent company is called NCSS, and that stands for something, but I can't remember what. They have a statistical package. I'm not familiar with their overall statistical software, but the PASS software is really helpful. It has a lot of different routines for just about any statistical technique that you would need to do a power calculation for. So I use that, and that guides me as to the things I need to know, kind of the inputs that go into that calculation. So, and they're all different based on the statistical technique that you're going to be using to analyze the data. So once you have that figured out, or with the help of a statistician have that figured out, then we talk about estimates that fit that statistical technique. And so there are a couple sources for those estimates. And again, as I just mentioned, published literature is one place to look. and oftentimes that's not very fruitful. Or at least people tell me nobody's ever done this before, which I sometimes I don't think I would question any of you all, but sometimes people who might be a little earlier in their careers, at times I have wondered if they were sure about that. But it is true. I mean, a lot of times people are looking at things that haven't really been studied in that exact way, and it can be tough to track down anything that would give you some guidance about what to expect. So where we most often end up is with these educated guesses. What do you think is going to happen? What do you think is going to happen in this group versus that group? What will the mean of this group be? What will the mean of that group be? And that makes some people nervous, but it really is okay. We're just trying to get in the ballpark. If a mean of 150 is very different from a mean of 5, so just put me in a ballpark and we'll be all right. It's not an exact science. A t-test example, again, as I've kind of already referred to, would be I would need to know something about what you thought the means would be in the two groups, and then what you think the variability is in those two groups. Because the more variability there is, the more different your patients or subjects are from one another, then the larger the sample size is going to need to be to sort of account for that variability. And so there are ways to help estimate that even when you have no clue what it would be. Because most people, I can't just throw a standard deviation off the top of my head. So I have some more questions I can ask that sort of help nail that down. And again, just to get in the ballpark. So there are actually also other ways to go about this. And it's, if the estimates aren't really getting where we want to go, then we'll look at some of these other things like how many patients do we have available? We may, does you and me no good if I say, well, you need 300 patients in each group, and in the last 9 years of electronic medical record data at Carilion, we only have 200 patients total that have that condition or meet those criteria. So knowing something about the volume of patients that fit your criteria is a good thing, and that's actually something that we can help you with. In the HEART team, we can look that up and kind of figure out that for you if that's not something you know already. Time, funding, those are both constraints that, again, if people have a fixed deadline for when their research project needs to be done, we have to be sensitive to that, right? I can't tell you, you need this many and that's going to take you 3 years and it has to be done in 6 months. So we try to be, reasonable about that and work with that, and it really all, comes out okay in the end. So what's nice is that with this software, I can very easily give you multiple scenarios. And so what I often do is say, well, if we assume this and this, you would need this many people in your sample. But if we change that a little bit, then the sample size goes up or it goes down, and you look at all these and tell me which one you like the best. And that's kind of how we end up settling on a sample size. Okay, so how are we doing on time? Not really well. Okay, so kind of from here on out is just kind of whizzing through a lot of different statistical techniques. I don't know, I may skip some things. I've talked a lot about t-tests already. Is that something most people are pretty familiar with? Just the concept of you have the mean of one group and a mean of another group, and you're comparing them to see if they're different. Because that would save me several slides to just kind of fly on past that. That's a fairly common thing that I think people generally kind of understand. So yeah, there are several different kinds of t-tests, and we're just gonna move along. So I guess one thing to mention though is knowing if you're going to measure the same patient, or if you're going to collect repeated measurements on the same patient over time. That also affects the choice of statistics. So if you're just looking at one point in time and you have one measurement of somebody's, whatever you're interested in looking at, that's kind of one. There are techniques that deal with that. And then if you're looking at, as in a paired t-test example, you have a pre and a post score on the same person. Sometimes, depending on what you're studying, you may have, 6, 10, 20, 30, like lab values or, whatever over time on the same person. And that has to be handled differently than if you just have one measurement on a person. So that also factors into how to analyze the data, because if we're looking at, let's just say, systolic blood pressure, my systolic blood pressures over a period of time are all going to be more similar to each other, hypothetically, than any of your systolic blood pressures. Because I'm me, all of mine should be pretty much the same and probably more similar than they would be to any of yours, because we're different people. So the statistics actually take that into account, and that's always sort of a factor. Okay, so real quickly, I don't want to spend a lot of time on correlation, because correlation is never going to be the end point, or the sort of the only statistical analysis that you would do in a study. It's a pretty weak technique overall, and it's almost more descriptive than anything else. I mean, it has a p-value attached to it, but it's just not a very, for most things, it's not a very confirmatory type of a technique to use. But there are a few things about it that are important, and so I'm just going to hit the highlights here. It's used when you have two continuous variables, and it helps you, I'm going to skip around a little, it helps you study the nature of the relationship between those variables. So you can have a direct relationship where they move in the same direction. As the values of one variable go up, the value of the other variable goes up. So age and weight, right? If you're looking from, like in kids, as they get older, they weigh more because they're growing, hopefully. So that would be a direct relationship. And then you can also have an inverse relationship, where as one variable goes up, the other one goes down. And so if we go back to the correlation coefficient, what I just discussed about the direct versus the inverse relationship, that is indicated by the sign of the correlation coefficient. So the R, Pearson's R is what it actually is known as, ranges from -1 through 0 to +1. Negative correlations indicate that inverse relationship, where one goes up, the other goes down. Positive correlations indicate that direct relationship, where they both move in the same. And then the number of the correlation coefficient tells us how strong the relationship is. So 0 is no correlation, no relationship. And the closer you get to either 1 or -1, then the stronger that relationship is. Typically, it's not considered strong until you get around 0.7 or 0.8, and that, in my experience, almost never happens, unless I'm not wanting it to happen, which is another sort of story. But generally, it's pretty hard to find two things that are strongly correlated with each other, just because in the real world, relationships are more complex than that, right? A lot of factors go into things, not just one thing fully being related to another, and that's the end of it. This is why it can be useful to look at correlation, but it's usually not the main technique that you would use in a study. There might be some exceptions to that, but for the most part, no. And then I'm pretty sure one of my statistics professors in graduate school made us take an oath, raise our right hand and solemnly swear that, correlation does not equal causation. So I'm sure you've heard that. Just throw that out as a reminder. And we will skip ahead. So this actually is probably maybe almost more relevant to some of the work we do because categorical data are pretty common, right? I mean, we have things like mortality, a lot of other, comorbidities and stuff like that can be conceptualized as yes, no. So we're often dealing with categorical data in the healthcare setting. And chi-square and logistic regression are two techniques that I come across in a lot of studies in my work here. So chi-square, or it's more computationally intensive cousin, I guess, Fisher's exact test, are used when your predictor variable and your outcome variable are categorical. And so a lot of times people come to me and say, I want to know, what percent of the people in this group had this outcome compared to this other group. And they're looking to compare proportions. And so that's when we kind of go in this direction of a chi-square or Fisher's exact test. Before computers came along, chi-square was really commonly used because it's very easy to do by hand. You could all do it by hand. It's not complicated and not even real long or involved. And so it was pretty popular, but it doesn't work well when you have a small sample size or if you imagine a 2x2 table with 4 cells, if one of those cells is 0 or is very small, that's what we call sparse data, and so that doesn't always work well for chi-square either. So Fisher's exact test is, there's a branch of statistics known as exact statistics, and what that implies is the computer can do lots and lots of iterations to arrive at an exact result that we couldn't do on paper. So it's an alternative for a chi-square for a 2x2 table, even when the sample size is small or when the data are sparse. So there's an example here of, do patients with Staph aureus who receive an ID consult have lower 60-day mortality compared to those same patients who do not receive a consult? And again, I'm just going to skip that for time. But this is an example of what your output would look like. And again, these are made-up data, really small. Most people would not only have 12 people in their study, so don't take anything from these numbers. But you can see, I kind of try to highlight these are the counts. So there were 5 people who did not have an ID consult and who died, 1 who did have a consult and lived, and then vice versa, basically, for the people who had, the 6 people who had an ID consult, 5 of them lived and 1 did not. And so then you have the row percentages and the column percentages, which are helpful for interpreting the results. These are the sort of the results tables, and I've put in red the things that you would most likely look at. So the chi-square statistic is the first one. This is the value of that statistic, and the p-value is 0.0209. So you would think, oh good, there's a significant difference, but then you come down here and at least in SAS software, this is what this is from, you get this warning that is saying, this basically is statistical mumbo jumbo for your sample size is not very big, you have sparse data, and chi-square, you might not want to pay attention to that. So then you can just go down here and check out the Fisher's exact test. And actually this is a case where the p-value is 0.08. So when you looked up here, you thought if you're using 0.05 as a cutoff, you thought, oh, I have a significant result. But then when you look at the Fisher's exact test, it's greater than 0.05. So you actually would not have a significant result because you'd have to go by this, and it's greater than 0.05. So this is an example of where this actually really comes into play and makes a difference because of that sparse sample size. Now, that's not to say that's what happens every time. It's just that this sample size was so small that I kind of manipulated all this so that it would come out this way. A lot of times, it'll be significant here and also significant here, or not and not. But for those times when they actually disagree, that's why we do Fisher's exact test, to be sure that we're getting the right interpretation. Okay, so I think we'll mostly just skip logistic regression. When people come to me and say, I have all these things and I wanted to know which of them predicts this outcome. I want to know, which things predict returning to the ED, or readmission in 30 days, or mortality, or whatever other thing. And I don't know what plays into that, and I'm trying to figure that out. That's when I start to think about a logistic regression type of question where you're using multiple predictor variables to predict an outcome and figure out, what combination of things leads to that outcome. So we'll just skip through all this. Big sample sizes for regression. It's pretty tough to do a regression with fewer than 100 people in your data set, and that's a bare minimum. So I think here, more is almost always better. I would say just keep that in mind. And yeah, so then this is an important slide, so I guess that pretty much wraps up the whirlwind tour of statistical techniques. But these are some of the different things that we can help you with. We really try to emphasize to people that we love to get involved early on. So again, once you know your research question, that's a great time to put in that request, or email somebody or call somebody over at the HEART team and say, hey, I need to meet with a biostatistician. And so we can help you with designing the study, with figuring out how your variables are measured, with figuring out your statistical technique, of course the power analysis, and then often we can help you get the data electronically and try to minimize the amount of any manual chart review that you have to do. We now have REDCap, which other people may have already talked to you about that, or I have a little bit of, I went through kind of our initial training for that, but that's been several months, so I can't tell you a lot of details, but it's a really great, pretty flexible and really secure system for storing data and being able to control exactly who can access it. So it's great for privacy, confidentiality, security, all that kind of stuff. And then very useful in terms of getting the data out and straight into SAS or whatever other statistical package that is being used. So REDCap is a big piece of data collection, and then we don't just run the analysis and then send you on your way. We try to interpret, help with writing, portions of methods, results, whatever, and doing any graphs or visuals that you might need for a poster or something like that. So we do a lot more than just crunch numbers, and so these are all things that we're happy to help you with. There are the names of people you can contact are all, of course, in the address book. I'll just point out that we have another Catherine Shaver at Carilion, and her middle initial is B. So she sometimes pops up first, and she very kindly sends me my email, but I am Catherine H. Shaver, so that would be who you would want to look for if you're trying to get a hold of me. And I guess that's it. We might have, I don't have to go right away, so if anybody has questions, feel free. And thank you for being here.